Hello and welcome back to the AICE Chemistry Lecture Series. In this video, we're going to be looking at Chapter 4, Section 8, which covers the last of the intermolecular forces, which we didn't cover in Section 7, that being hydrogen bonding. Now, hydrogen bonding is a very unique type of intermolecular force, and it plays a huge role in a lot of natural processes. So let's get started. Hydrogen bonding in itself is actually just a strong type of permanent dipole force. Hydrogen bonds are the strongest of all the intermolecular bonds, and it's just a specialized type of permanent dipole force which requires a specific element to be bonded to hydrogen. In the case of hydrogen bonding, there are three different elements that can undergo hydrogen bonding, and that's fluorine, oxygen, and nitrogen. So whenever in a molecule we have hydrogen, let me make that a little smaller, hydrogen bonded to fluorine, hydrogen bonded to oxygen, or hydrogen bonded to nitrogen, any of these three bonds present in a molecule will indicate that that molecule will have hydrogen bonding as one of its intermolecular forces. The reason why this is the case is because fluorine, oxygen, and nitrogen are the three most electronegative elements. So they form the most polar bonds. So again, this is just another type of permanent dipole force because it is a force happening in polar molecules. But those polar molecules have one of or multiple of these three specific types of bonds in them. Now, when hydrogen bonding, these molecules will bond to our hydrogen bond to other molecules with the same intermolecular force, meaning with that hydrogen bonding or one of these three bonds. When they do so, though, they need to connect to a lone pair of electrons. So we can see here, for example, in the case of ammonia, hydrogen bonding ammonia, we have that nitrogen-hydrogen bond, which indicates to us that ammonia can undergo hydrogen bonding. When ammonia undergoes hydrogen bonding with another ammonia molecule, the hydrogen bond represented here by these red dots happens between the hydrogen of one ammonia molecule and the lone pair of another. The reason why is because the ammonia molecule, like we said, is a polar molecule with the hydrogens being partially positive and the nitrogen being partially negative. When we have that lone pair of electrons becomes even more negative because lone pairs of electrons are already negative. So the polarity of the bond combined with the lone pair of electrons makes this area really partially negative, attracting the partial positive hydrogens in the other molecule. And that attraction is what we call the hydrogen bond. So hydrogen bonds happen between the hydrogen in a HF, HO, or HN bond to the lone pair on either F, O, or N on another molecule. Even though you don't need to know this specifically, the strength of a hydrogen bond is around 1/10 that of a covalent bond. So hydrogen bonds, this is a misnaming of the force, obviously. Hydrogen bonds are not bonds, they're intermolecular forces, but they're called hydrogen bonds because they're the strongest of the intermolecular forces and require hydrogen in order to happen. So there's a lot of common molecules that will have hydrogen bonding. Ammonia being one of them, water, any of the hydrogen halides, so any halogen bonded to hydrogen. A lot of organic compounds are biochemical compounds like DNA and proteins have hydrogen bonding, and it plays a key role in a lot of natural processes. Now, let's look at the number of hydrogen bonds a molecule can form. Now, when we talk about the number of hydrogen bonds, what we are looking at here is an average per molecule. The average number of bonds per molecule that ammonia can have, for example, is 1. The reason being that a hydrogen bond requires two things. It requires the molecule to have the fluorine, oxygen, or nitrogen present in one molecule. And then it requires lone pairs on the other molecule. Because of this, because hydrogen bonds happen between a hydrogen in one molecule and a nitrogen in another, when we look at ammonia, even though ammonia has 3 hydrogens, it only has 1 lone pair of electrons. So it can only form, on average, 1 hydrogen bond per molecule. Now, you might be saying, but there are 2 other hydrogens here. Those could form hydrogen bonds. And that is true. That hydrogen could form a hydrogen bond to a different lone pair. But that would be taking away a hydrogen bond that a different molecule can do. So what we have to realize here is that when we talk about the number of hydrogen bonds per molecule, it is an average of all the molecules in the sample, not actually per molecule. Because if a molecule does happen to form 2 hydrogen bonds, that hydrogen bond is taken away, taking the lone pair on another molecule that could be used by a different ammonia molecule. The compound that can usually form the most hydrogen bonds will be any compound that has oxygen, fluorine, or nitrogen with 2 lone pairs of electrons. Because of how bonds work and how valence electrons work, that means that only molecules that have oxygen in them can form 2 hydrogen bonds on average per molecule. Water is a prime example of this. Water can form 2 hydrogen bonds on average per molecule because it has 2 hydrogens and 2 lone pairs. This makes the hydrogen bonds formed by water particularly strong because they can form more of them. Whichever number is the lowest between these two that we talked about, between the lone pairs and the F over N, whichever number is smaller, that's going to dictate how many hydrogen bonds you can make. In the case of ammonia, because we only have 1 lone pair versus 3 hydrogens, that 1 lone pair detects that we can only have 1 hydrogen bond. In the case of water, because we have 2 lone pairs and 2 hydrogens, we can then form 2 bonds. Now, like I said, hydrogen bonds do play a key role in the properties of any compound that has hydrogen bonding. We can especially see this in the boiling point of hydrogen bonded compounds. When we compare the boiling points of compounds that have hydrogen bonding to their counterparts in the same group, we can see a very, very obvious difference. For example, if we look at group 17 elements, so we're going to focus here on this blue line first, and then we'll do the red line. So if we focus on the group 17 elements, iodine, bromine, chlorine, and fluorine. If we look at the hydrogen halides of those elements, we have spoken about this before, but again, breaking down that word, hydrogen halides. Hydrogen is pretty self-explanatory. It's anything with hydrogen. Halides meaning halogens. So hydrogen halides are compounds made between hydrogen and a group 17 element or a halogen. So HI, HBr, HCl, HF are all hydrogen halides. If we look at the trends for hydrogen halides in blue, we can see that HI, HBr, and HCl have a trend where as we go down the group from row 2 to row 3 to row 4, the boiling point is going to increase. Well, if this pattern kept going, then we would expect HF, which is in row 1, to have the lowest boiling point. But in fact, it has the highest out of all the hydrogen halides. When we look at the same trend for group 16 elements, we see the same thing. Row 2, sulfur, row 3, selenium, and row 4, tellurium, when combined with hydrogen, have an increasing boiling point as you go down the group. So we would expect row 1, oxygen with hydrogen, being the lowest. But we see here that water actually has the highest boiling point out of anything in this chart. And the reason is pretty simple. It's the difference between the intermolecular forces. Water and hydrogen fluoride, HF, have hydrogen bonding in them. We have oxygen bonded to hydrogen and fluorine bonded to hydrogen in these molecules. Whereas the counterparts of the groups, HCl, HBr, and HI for group 17, H2S, H2SC, and H2TE for group 16, don't have hydrogen bonding because we don't have fluorine, oxygen, or nitrogen. We instead have permanent dipole forces and London dispersion forces in these compounds. So why are these compounds increasing in boiling point, but then H2O and HF are higher? That's because H2O and HF have hydrogen bonding. So again, we're comparing things that are different versus the permanent dipole bond intermolecular force that we have in the lower elements in those groups. Now, why do these increase? Just to recap from the last chapter, remember that even though these are all polar, we're not going to compare their strength in polarity. They get higher in boiling points because they have more electrons as we go from row 2 to row 4. More electrons means stronger London dispersion forces, because we're not going to compare their strength of their polarities. If they're all polar, if they all have PD or permanent dipole forces, we compare their London dispersion forces or instantaneous dipole forces. They have more electrons as we go down the group, therefore they get stronger London dispersion forces, and so their boiling point increases. So again, we can see that in a much clearer form here. As we go down the group from row 2 to row 3 to 4, there's a difference in instantaneous dipole-induced dipole forces, or London dispersion forces, because we get more electrons. But this is not the case with H2 and HF. Even though they have the least number of electrons, what they have is hydrogen bonding, which is the strongest type of bonding. Now, properties of water. So because water has hydrogen bonding, water has very unique properties that are the reason why life depends on water so much. Most of the properties of water are due to those hydrogen bonds that are created in water, and to the fact that water has more hydrogen bonds than most other molecules with hydrogen bonding in it. If it wasn't for these particular unique properties of water, we would not be able to survive on Earth. Water is a key part to why life happens on Earth. So we're going to start by talking about the boiling point and the enthalpy change of vaporization. Now, the enthalpy change of vaporization and the boiling point of water are higher than most similar compounds. Now, what are these two? We already talked about the boiling point of water, and I'm going to make a very clear point of outlining what these things are. The boiling point of water is the temperature at which water boils. Now, this is related to the enthalpy change of vaporization, but it is not the same thing. The enthalpy change of vaporization, enthalpy change means energy change. The enthalpy change of vaporization is the amount of energy needed to boil water. We'll discuss this a lot more in chapter 6, but the amount of energy needed to transform 1 mole of liquid water, or 1 mole of any liquid really, to gas. So whereas boiling point is talking about temperature, the enthalpy change of vaporization is talking about the amount of energy needed to grab 1 mole of that liquid and turn it from liquid to gas. This, we're talking about specifically with water right now, but this could be enthalpy change of vaporization, could be a property of any liquid. So what is the difference between these two? They are related. The higher the boiling point, the higher the enthalpy change of vaporization. But they are different measurements. The boiling point is the temperature at which it happens. The enthalpy change of vaporization is the amount of energy needed to transform that 1 mole of a liquid to a gas. So one deals with a threshold, at what point does it start happening? The other one deals with an amount, the amount of energy needed to do that process. The enthalpy change of vaporization and the boiling point are higher for water than most liquids, most covalent molecular liquids, because of the strong hydrogen bonds that require a lot more energy to break, and therefore a lot more energy to go from the liquid state to the gas state. If it wasn't for this property, then liquid water wouldn't exist on Earth, which will make it really hard for life to begin. Surface tension and viscosity are another property that are going to be due to the boiling point of water, or to the hydrogen bonding in water. Hydrogen bonds in water reduces their ability to slide past each other, which makes them more viscous. Viscosity, if for those of you who are not aware, is the ability of a liquid to flow. So some things that are very viscous or have very high viscosity, for example, are things like maple syrup or honey that you're familiar with. Things with low viscosities are things like oil and, really any kind of oil. So viscosity talks about how likely are these molecules to slide past each other in a water droplet. On the other hand, surface tension is related to viscosity, but not the same thing. Surface tension is the ability of a liquid to stay together. So you might be familiar with whenever it rains and you have water droplets in your car. The droplets after it's done raining kind of form a dome. They don't flatten out when you have water on a surface. They domes into little droplets. And this is because of the surface tension. It's the ability of water molecules to interact with each other and keep each other together because of the hydrogen bonds in that water. Those hydrogen bonds keeps these molecules together, which allows them to, one, retain their shape, but two, also counteract the force put on it. You might have also heard that if you fall from the 20th story into water, it is the same as hitting concrete. And that is because of surface tension. Because water wants to stay together, it takes a lot of force to separate water molecules, since the hydrogen bonding keeps them together. The surface tension is the reason why falling into a river from let's say 200 feet in the air is the same as hitting concrete, because the water molecules will not separate fast enough, because hydrogen bonding is keeping them together. Finally, and probably most importantly to life on Earth, is that the fact that ice is less dense than water. Unlike most chemicals, ice is less dense than water. Most chemicals, the solid is more dense than the liquid. And this is due to the hydrogen bonds in ice creating what we call a honeycomb pattern or a hexagonal lattice. When water molecules come together to form ice, the hydrogen bonding puts them at certain angles, which create this honeycomb or hexagonal patterns in its lattice. Because you have so much space between the water molecules, because there's so much empty space or these pockets in the structure, that ice is actually less dense than water molecules when they're in the liquid state, which are really close together. And so ice becomes less dense than water. Why is this important to life on Earth? If this wasn't the case, if ice didn't float on water, whenever water freezes, it will sink to the bottom, and it will essentially create a situation where the whole lake or a whole ocean or a whole river would freeze. Unlike what actually happens now, because ice is less dense than water, if we have, let's say, a body of water like an ocean or a lake, I'll draw it up here actually. So if we have a lake filled with water, as the water freezes, only the top layer of water is going to freeze. And because that ice that's created floats on top of the liquid water underneath it, this water all being liquid, it creates an insulating layer of ice, keeping all that water liquid. So if you have something like a fish in this lake, that fish will not die because the water doesn't freeze solid. Those fish or whatever life is in that water can actually survive below the ice layer. Whereas if this whole pond or lake froze over, all of those fishes will die, and then we will have never gotten past the point in evolution where life went from the ocean or from water bodies to the land. So again, these are the important properties of water that are unique to water because of the hydrogen bonding. You should be able to relate the physical properties of water, and realistically speaking any chemical, to that of their intermolecular forces and be able to connect the two. And let's look at a question like that. So in this question from paper 2, it says state, not explain, just state, one physical property of ammonia which is caused by its polarity. So ammonia, again being NH3, means that it's going to have, as far as intermolecular forces are concerned, hydrogen bonding because it is polar and it has nitrogen-hydrogen bonds. So because it is polar, so based on its polarity, and because it has hydrogen-nitrogen bonds, it will have hydrogen bonding, which means we can pick any of the physical properties that are improved by hydrogen bonding to answer this question. The main one, the one that is usually the prime example, is boiling point. Boiling point is going to be high. That is a physical property of ammonia that is due to its polarity. Now, what you don't want to say is don't get physical properties confused with chemical ones. Being more reactive is not a physical property, and therefore is not an answer to this question. So do be very careful with the difference between physical properties, boiling point, melting point, viscosity, surface tension, that kind of thing, versus a chemical property, which is the ability to react. So here's what our mark scheme says. It says ammonia has a higher boiling point than expected from the molar mass value, or has a higher boiling point than methane, for example, methane being the comparable or a comparable molecule of similar size, or NH3 soluble in water. Solubility is another property which we didn't discuss very much, but you can use it. Solubility is a property of water given by its polarity because polar molecules will dissolve in other polar molecules. So NH3 being polar means that it will dissolve in water, which is also polar. But boiling point is usually the better answer here whenever they ask you all the properties of a molecule based on its polarity, because it's a physical property that's directly correlated to it. Notice, did we use the words hydrogen bonding? No, you didn't need to. Why? Because the question was state one physical property of ammonia which is caused by its polarity, not its intermolecular forces. Had we needed to say intermolecular forces, then we would have needed to say hydrogen bonding. But because it is not based on intermolecular forces, it's based on polarity, yes, it is due to hydrogen bonding that has a higher boiling point than expected, but we can get away without using the term hydrogen bonding. All right? And that is it. That is the last of the intermolecular forces. That is it for section 8, and I will see you in the next video.